Good morning, students. And as you know, nowadays in these videos we are doing number theory, and the topic which we are covering is congruences. And today I'm going to start with the residue system. What are residue? What is a residue system? What is complete residue system? What is reduced residue system? What are their properties? What are the theorems related to reduced residue system and residue theory, in fact. So let us start with what are residues. So the first thing you should know is what a residue is. So let m be any positive integer and let a be any integer. Then B is said to be a residue of R, said to be a residue of A modulo M if A is congruent to B modulo M. This is the basic definition of residue. For example, suppose you know that modulo 7, 32 is congruent to, you can say, 18. 32 is congruent to 18 modulo 7 because 7 divides 32 minus 18, that is 14. 7 divides 14 is well known. So from here you can say that 18 is a residue. 18 is a residue of 32 modulo 7. This residue modulo 7 of 32, it is not unique. It's very obvious because you can replace this 18 by 11. 7 also divides 32 minus 11, that is 21. So 11 is also a residue of 32 modulo 7. Similarly, you can have 4 here. So 4 is also a residue of 32 modulo 7. So there are infinitely many residues of a particular number modulo a particular number m. And if you collect all these numbers, then it is said to be a residue system of A, or the residue class of A. For example, here we are working with 32. So what is E32? E32 means residue class of 32 modulo 7. So you will have here you will have here 4, 11, 18, 25 and so on, because we are working here modulo 7. In other words, you can say that this E32 is nothing but 4 plus 7k, where k is any integer. This is, we are doing modulo 7. So any number of this type, because 32 is congruent to 4 plus 7k modulo 7. It is very much clear. So this is the residue class of 32. Similarly, you can create, you can construct, you can write residue class of any integer. So if somewhere we are writing EA modulo M, that means we are considering the set of all those integers which when divided by M will leave a remainder which is congruent to A modulo M. So this is the class EA. Secondly, if you are working with modulo m, then there will be exactly m residue classes. What these classes are? So let us have, suppose your m is 7, then how many residue classes will be there? Exactly 7. And which these classes are? These are E0, E1, E2, E3, E4, E5 and E6. Because if you will move next to E7, then E7 is nothing but same as E0. Because 7 is congruent to 0 modulo 7. Similarly, if you are talking about E25 here, then look, 25 is congruent to which of these numbers here? Modulo 7. So definitely 24 is congruent to 4. So 25 is congruent to 4 modulo 7. That means your E25 is same as E4. You can have a look. What is E4 first of all? In E4 you will have 4, 11, 18, 25, 32 and so on. These numbers will be there in the class, residue class of 4. But these are also the elements which are in the class 25. Why? You take any one of these, suppose you are taking this, then this 25 is congruent to this 32 modulo 7 also. So that means 32 also belongs to the class of 25. It belongs to the class of 4. So if you are working with modulo m, then there are exactly m residue classes, namely E0, E1, E2, E3 up to em minus 1 in general. Here I am talking about E7, so the last class is E6. Otherwise, in general you can say em minus 1. These are residue classes, not residue system. What residue system is, we will discuss later on. But before moving on to the residue system, let us have some typical properties of these residue classes. So what these properties are? For any m belonging to z, that means for any integer z, m, we have some properties which we are going to prove as well here. The first one is EA is equal to EB if and only if A is congruent to B modulo M. This is the first property which we will prove here today. Secondly, I am writing it here because I am lacking the space. I want to write the proofs also here. So second one is X and Y belong to the class of A if and only if X is congruent to Y modulo M. This is the second one which we will prove here. The third one says that E0, E1, E2, Em minus 1 are pairwise disjoint. And the most important is that union of these EIs, when I vary from 0 to m minus 1, that means union of all these is nothing but the set of the set of integers. So these are the four basic properties of residue classes which we are going to prove in this video, and then we will do some more properties as well before leaving this video. So what are the proofs? Let us move on to the proofs of these properties. The first one is that, so here you are having if and only if. And you know that when there is if and only if, then you are to prove directly as well as the converse part. So first, suppose that EA is equal to EB. Let EA is equal to EB, and what we are to show that A is congruent to B modulo M. We are to show that to prove A is congruent to B modulo M. This we are to prove. Let X be any integer which is in EA and is EB also, because EA and EB are same. Look at your X is in EA. Your X is in EA. So if X is in EA, that means your X is congruent to A, or you can say A is congruent to X modulo M. And once again, leave this one and look at this, that your X belongs to EB. And X belongs to EB means X is congruent to B modulo M. Now, read it like this. X is congruent to A means A is congruent to X. Why? Because the congruence property is symmetric in nature. Now look at these two. A is congruent to X modulo M and X is congruent to B modulo M. And we know that the congruence relation is also transitive. So if A is congruent to X and X is congruent to B, then from transitivity we can have A is congruent to B modulo M, which was required to be proved in the direct part. And now we'll move on to the converse. Conversely, suppose that A is congruent to B modulo M. And what we need to prove? We need to prove now that EA is equal to EB. What are EA and EB? EA is a set. EB is also a set. And if we want to show that these two sets are equal, how we will show? We will show that this set is a subset of this set and this set is a subset of this set. A is a subset of B, B is a subset of A, means A is equal to B. So first we will show that EA is a subset of EB. For that we will take one element from EA and we will show that that element belongs to EB, and that will prove that EA is a subset of EB, and similarly we will do it other way. So let X belongs to EA. If X belongs to EA, by the definition of EA, your X is congruent to A modulo M. But we are given that A is congruent to B modulo M. A is given to be congruent to B modulo M. And now use transitivity once again. X is congruent to A and A is congruent to B. If X is congruent to A and A is congruent to B, this directly means X is congruent to B modulo M. And if X is congruent to B modulo M, then X belongs to the residue class of B. You have taken X from EA and now X is in EB, which means your EA is a subset of EB. And let us move other way on the same lines. Now suppose your X is in EB. What will happen? If X is in EB, your X will be congruent to B modulo M. And we are given that A is congruent to B. And we know that the congruence relation is a symmetric relation. So A is congruent to B can also be written like B is congruent to A. Once again use the transitivity. X is congruent to B and B is congruent to A. That means X is congruent to A. X is congruent to A modulo M means X belongs to EA. You have started with X belonging to EB and now X is in EA. That means EB is a subset of EA because every element of EB is in EA. So that means EB is a subset of EA. Already we have shown that EA is a subset of EB. EA is a subset of EB and EB is a subset of EA. That means they are same. EA is equal to EB, and that was what required to be proved in the first part. So first part is proved directly as well as conversely. Now we will move on to the second part of this theorem, or you can say property. What the second part is? In the second part, x, y belong to EA if and only if. Once again, we are having if and only if. So that means direct proof as well as converse proof is needed. So suppose let your x and y are in EA. What you have to show that x is congruent to y modulo m, and the proof is very easy. Take these one by one. X belonging to EA, y belonging to EA. X belonging to EA means x is congruent to A modulo m, and y belonging to EA means y is congruent to A modulo m. And we know that congruence relation is reflexive, symmetric, transitive. So using symmetricity, this y is congruent to A, you can write A is congruent to y. Now x is congruent to A and A is congruent to y. Use transitivity now to get x is congruent to y modulo m, which was required to be shown. So direct proof is okay. Now we will move on to the converse. Conversely, we will suppose that x is congruent to y mod m. So let x be congruent to y mod m, and what we are to prove now, that x and y both are in the same residue class. EA means same residue class. Maybe EB, maybe EC, maybe ED, any class, but x and y are both in the same residue class. So suppose x is in EA, and then we will show that y also belongs to EA. Let x belongs to EA. So what we are to show now, that y also belongs to the same class EA. X belongs to EA means x is congruent to A mod m by definition of residue classes. X is congruent to A. You read it reversely, or whatever is given is x is congruent to y. So x is congruent to y, you can say y is congruent to x by using symmetricity of the property. Y is congruent to x and x is congruent to A, and use transitivity now on these two. So you will get y is congruent to A mod m, and y is congruent to A mod m means y belongs to EA. You have taken x belonging to EA, and now y also is in EA. That means x and y both are in the same residue class, and that was to be shown in the second part. Now moving on to the third part. Third and fourth part are really very important, useful for upcoming theorems, properties, articles and lemmas. So what is the third part now? We have to show that these E0, E1, E2, EM minus 1, these are pairwise disjoint. So I'll take any two of them. I'll suppose they are distinguished, they are not same, and then I'll show that they are disjoint. Their intersection is 5. So let EI not equal to EJ, where both I and J, they are greater than or equal to 0 but less than or equal to m minus 1. Obviously I is not equal to J because EI is not same as EJ. So this I have considered. Suppose if possible, their intersection is not phi. In fact, we have to show that their intersection is phi because we have to show that they are disjoint. I have supposed their intersection is not phi. So definitely I will arrive at some contradiction, and that will prove that their intersection is phi. If the intersection is not phi, they must have some common element. So let x be the common element. Let x be the common element of EI and EJ. So this means x belongs to EI and x belongs to EJ. This means x is congruent to I mod m, and here you can say x is congruent to j mod m. Once again, as we are doing in previous parts of this theorem, x is congruent to j, you can write j is congruent to x by using symmetricity. And now use transitivity. You can use transitivity. You first read this and then come on to this. J is congruent to x and x is congruent to I. J is congruent to x and x is congruent to I means j is congruent to I. J is congruent to I mod m. That means m divides j minus I. Whereas your j minus I mod strictly lies between 0 and m. It is greater than or equal, it is greater than 0 because I and j are not same, so it cannot be 0 even. J minus I mod is strictly greater than 0 and is strictly less than m and is divisible by m, which is not possible, which is impossible, and it is a contradiction. A number which strictly lies between 0 and m cannot be divisible by m. So we arrive at some contradiction, and why this contradiction is there? Because our supposition was wrong. And what we have supposed? We have supposed that their intersection is not 5. So that means EI intersection EJ must be equal to 5, and that means these E0, E1, E2, E3 up to EM minus 1 are pairwise disjoint. So third part has been covered, and now we are moving on to the fourth part of this theorem. In the fourth part, we have to show that union of all these pairwise disjoint residue classes is nothing but the set of integers. Each of these EIs, whether it is E0, E1, E2, EM minus 1, everyone is a subset of Z, no doubt in it, because EI contains only integers. So EI is a subset of Z for every I greater than or equal to 0, less than or equal to m minus 1, it is okay. What we are to show that Z is also a subset of EI for some EI, and that means they will be equal. But before going to that, EI is a subset of, every EI is a subset of Z. So definitely their union is also a subset of Z. If each EI is a subset of Z, their union must also be a subset of Z. And now we have to show that Z is a subset of union of this. For that, I will take one element from here. So let x be any integer. X be any integer. If you divide x by m, whatever the quotient you are going to get is not a problem, but the remainder, whatever the remainder r will be there, it is definitely greater than or equal to 0, but less than or equal to m minus 1. So that means your x is congruent to r. X is congruent to r modulo m for some r belonging to the set 0, 1, 2, 3 up to m minus 1. Now, if your r is 0, then x is congruent to 0, means x belongs to E0. If your r is 1, x is congruent to 1 modulo m, that means x belongs to E1. If your r is 2, x is congruent to 2 modulo m, x belongs to E2, and so on. If your r is m minus 1, then x is congruent to m minus 1 modulo m, means x belongs to m minus 1. So that means whatever the value of r is, your x is in some of these residue classes. So this means x belongs to EI for exactly one I belonging to 0, 1, 2 up to m minus 1. So that means X is in E0 or in E1 or in E2 and so on, or in M minus 1. So wherever X is, if X is here, even then it is in union. If X is in E1, it is in union. If X is in M minus 1, it is in union. So your X will be a member of union EI. I vary from 0 to M minus 1. You have taken X from Z and X is coming out to be in union EI. I varies from 0 to M minus 1, means your Z is a subset of union of EI. I vary from 0 to M minus 1. And earlier we have seen that union is a subset of Z and now Z is a subset of union, so they must be equal. That means union of EI, I vary from 0 to M minus 1 is nothing but the set of integers. So these are some properties related to the residue classes. And next we are moving to residue system. Till now we are working with residue classes, not residue system. And now we will work on residue system. But I am going to stop this video here. In the very next video we will discuss residue system, complete residue system and reduced residue system. Till then, thank you once again.